All right. Hey, AP Chemists. So in this lecture, part 4, I believe it is, we're going to be talking about electron configurations. Here are the answers to C and D for you to check from the previous lecture if you needed to check your answers here. We're actually going to start from here. Now, in my last video, I talked about energy level diagrams, and then there's an order. And in class, we'll talk more about, or we have talked about, how we put electrons in orbitals. We have these 3 rules here. I want to remind you, and you could write yourself a little note here, that we have orbitals where electrons are found, right? So this little dash right here is like an orbital where electrons are found. The s orbital, there's only one of them in each energy level. They could hold up to 2 electrons. The p orbital, there are 3 of them in each energy level. That holds up to 6 electrons. And the d orbital, there are 5 of them in each energy level. That could hold up to 10 electrons. So that's very important for us to know. Now I want to go from an answer to electron configuration. So let's look at our answer to choice C, or sample C here. I kind of already did it for A and B. This is the beginning of what we're going to be learning as how to write an electron configuration, right? It's going to have this 1s2, 2s2, 2p6 going on. All right, so let's look at how I'm going to go from here to an electron configuration. So look here. This is known as the 1s orbital. It's the s orbital in the first energy level. There are 2 electrons in this s orbital in the first energy level. This we'll label as 1s2. Notice you'll see I put 1 as the energy level, s is the orbital, 2 in the top here is the total number of electrons. I'll continue on. The next one up is the second energy level, 2. It's in the s orbital. There are 2 electrons, 2s2. Look at that. 2s2, the second energy level, s orbital, 2 electrons. We're not done though. In the second energy level, we still have this p orbital or set of orbitals. So it'll be 2p, and then we have 1, 2, 3, 4, 5, 6, 2p6. I'm going to keep on going up. We have 3s. There's 2 of them. And then finally, we have 3p, but there's not 6 in there. There's 1, 2, 3, 4, 5. 3p5. All of these together will make our electron configuration: 1s2, 2s2, 2p6, 3s2, 3p5. All of these numbers in the top add up to 17, which is the number of electrons in the chlorine atom. The electrons are going to be equal because it's chlorine. And we could do the same thing for vanadium. I'll do the same thing. We'll have 1s2, 2s2, 2p6, 3s2, 3p6. Now it goes to 4s2. This is weird. The 4s is below just a itty bit the 3d. And this is 3d3. So vanadium will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. That was a long one. Altogether, 23 electrons. All those numbers in the top. So you could see here that these numbers on top, these powers, these superscripts, they are the electrons that are in those orbitals. This is how you write an electron configuration. We get it from the energy level diagram to electron configuration. Something else that I did want to make note of, you might see questions in the future about paired and unpaired electrons. Well, remember, we could write electrons in an orbital like this. This is known as a paired set of electrons. So you could see that in the 3p of the chlorine here, oops, I don't know why I did that. In the 3p of the chlorine here, there is 2 paired, 1 unpaired. You could have 1 up, and that'll be called an unpaired electron. You could have 1 up and down together. We call that a paired electron. Look at the 3d of our vanadium here. There are 3 unpaired electrons. The chlorine here only has 1 unpaired electron. Just doing some vocabulary and nomenclature, and we'll talk more about this in class, but just throwing it out there. All right, so here are some more notes on electron configurations. I'm not going to spend too much time on this, but just a couple of things. We call ground state electron configurations as the one with the lowest energy, meaning we used Aufbau principle. We go from low to high. So we don't, without skipping. That's what we mean by ground state electron configuration. In class, we'll learn about excited state, but I just want to make sure that we know that. We can write down each orbital in the order they appear in the diagram, which is exactly what we just did. Add superscripts to indicate the number of electrons. So that's a lot of underlining there, but I'm going to actually go back and just highlight all of this here. So this is what we just did. We can write down each orbital in the order they appear, and the subscripts is the total number of electrons in each orbital. I did that at the top here. And just to elaborate a little more, for example, hydrogen only has one electron. So if I were to do the orbital diagram for hydrogen, it would just be 1s, boop, one unpaired electron. That would become 1s1. Sometimes we don't want to or have to draw out the orbital diagrams. That's too much work. If you remember the order, and the order was from our previous notes right here, here is this order where I said, OMG, you need to know. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. And if you know how many are in each orbitals, then you'll know how many you could put in each orbital. So 1s, then 2s, and 2p, then 3s, 3p, 4s, 3d, so on and so forth. And then the s could have up to 2, p's can have up to 6, S2, D can have up to 10. So just like, this would be like maximum here. So just doing that as an example. Here's another example, ground state electron configuration for fluorine. Fluorine only has 9 electrons. We could do an orbital diagram, or I could just keep on going. I could do 1s2, 9 minus 2, I got 7 left. The next one is 2s2 minus 2, I got 5 left. The next one after the 2s is the 2p, I got 5 left. I could put 6 in the p, I have 5, I could put all 5 in that p. 1s2, 2s2, 2p5. And then we already did the electron configuration for chlorine. It matches the one that we did here. So I'm going to put this arrow here, but I'm going to erase it next. But you could see that this is the same thing, right? 1s2, 2s2, 2p6, 3s2, 3p5. Just going a little quick there. We could use the periodic table also to help us, and this is a nice little trick. Elements in groups 1 and 2, so group 1 and 2, they typically end in an S. Elements that are in the middle, like our transition metals, they end in D. They end in the D orbitals. And then elements that are in groups 3 through 8, they end in the p orbital. And that's like a nice little trick for us. So if I'm looking on the periodic table right here, let's say this is fluorine. Fluorine is going to end in 2p. But below fluorine is chlorine. Chlorine is going to end in 3p. Below chlorine is bromine. Bromine is going to end in 4p, and so on and so forth. So that's a nice little trick for us to remember. And look, I have them kind of drawn out here. So if I'm looking at groups 1 and 2, let's say whatever element this is, let's say this is magnesium. Magnesium's going to end in 3s2. And the way that I like to try and figure out electronic configurations is just by kind of adding up all of the electron configurations from this little trick here. So for example, if I was trying to get silicon, which I'm going to circle right here, right, I would do like 1s2, then 2s2, then this would go to 2p6, then 3s2, then 3p2. So if I was going to do silicon, I would have all the way up to 1s2, then 2s2, all the way up to 2p6, then 3s2, and it ends in 3p2. So I'm not going to elaborate more on using this little trick. This is a trick that we could talk more about in class, and I'll have other supportive videos for you to do that. The last thing I'll talk about in this video is using something known as abbreviated or noble gas electron configuration. Elements in group 8 are known as noble gases, so like helium, neon, argon, krypton, xenon. They end in full shells. I'm going to call that in quotes, meaning they go up to the S2 or the P6 or the D10 if it was going to be that way. They go up to the S2 and the P6. They are completely full. Sometimes if I write a really long electron configuration, let's say I'm a chemist and I'm trying to save myself time and space here. Instead of writing out this really long electron configuration, I will notice that neon's electron configuration is 1s2, 2s2, 2p6. So any elements that have this beginning electron configuration, I could just remove it from the electron configuration and write neon in brackets. Oh, why is it not letting me write anymore? Here we go. It's writing neon in brackets. So here would be the noble gas configuration for chlorine. It would be neon in brackets because the beginning of this electron configuration is the same here. And then end with whatever's remaining, 3s2, 3p5. I'll do another one just for simplicity. Like let's say I was going to do helium as a noble gas configuration for another element. Let's say I was going to do carbon. Well, earlier I showed you the electronic configuration for carbon. Carbon has 6 electrons. So 1s2, there's 4 electrons left. 2s2, there's 2 electrons left. 2p2. All right, now helium is 1s2. Helium is 1s2. The beginning of carbon is 1s2. So I could write the noble gas configuration of carbon as helium, right? Kind of just showing you that, oops, I don't want to erase that. Showing you that orange here is 1s2. And then I'll write the rest, 2s2, 2p2. Boom, that would be the noble gas configuration for carbon. Alrighty, so we've reached the end of the video here. If you want to stop, we're done. For effort, you could either write down these notes and turn this in, or try and complete sample problems 10 through 12. I'm going to get us started on just number 10, and then I'll end the video officially. So it says, what is the ground state electron configuration for NNO? I already wrote on the side here that nitrogen is 7 electrons, oxygen is 8 electrons. Well, remember, we have the orders 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, dot, dot, dot. Remember that S can have, I'm going to use a different color, S can have up to 2, P can have up to 6, and D can have up to 10. So I'll do nitrogen. 1s2. That is 2 of the 7 electrons. I have 5 left. I'll do the next one. 2s2. That's 4 of the 7 electrons. I have 3 left. 2p3. Done. Alrighty, we are going to do more practice and more support in class. This is just the beginning. For your efforts, you could continue doing on 10, 11, and 12 and turn those in, or you could turn in your notes.